Welcome back. And in this video, we're going to be looking at pH titration curves. So we're going to be plotting the volume of sodium hydroxide or acid added versus the pH for different types of acid and base combinations. So you're going to need your notes, and we're starting on page 8. So in class, you're going to do an experiment where you're adding sodium hydroxide to a solution of acid and you're measuring the pH. So sodium hydroxide, that is a strong base, and HCl is a strong acid. Remember, strong and weak have nothing to do with concentration, it's to do with the amount of dissociation or ionization. So sodium hydroxide completely ionizes, as does HCl, so they're both strong. And when you plot one of these curves, this is the kind of graph that you should see. So there's a long flat bit, there is a steep vertical section over a large pH units, and then there's another section here. Now the equivalence point we take as being the middle of that vertical section. So at that point, that's when we say the concentration of the hydrogen ions equals the concentration of the OH negative ions. And at that point, that's the end point of our titration, and we can read off here the volume. Now, because it's a 1-to-1 molar ratio, we would expect that to read 25 centimeters cubed, which it does. You need to be able to sketch these curves. So a couple of things to point out. Starts at 1. End point, equivalence point, is the midpoint of that vertical section, which for a strong should be 7, and it ends up around about pH 13 to 14 at the end. And this is a very large or long vertical section. We can see the same sort of thing, but this time for a strong base versus a weak acid. And we get a similar looking curve, but it does have some significant differences. So for a start off, it starts around about pH 3. Again, it will end up at around pH 13. Notice the vertical section is much shorter, it's about 2 or 3 pH units less than that. And the end point of the curve, the middle point of this vertical section, reads off at about pH 9 rather than 7. And it has this very important buffering region here. Remember, buffer is a weak acid and it's salt. And here we have a weak acid and we've made quite a large proportion of the salt. So our starting pH for this strong base weak acid is about pH 3. So that depends upon the concentration of the acid, but also it depends on the Ka, or the degree of dissociation. Obviously, the more concentrated the acid, the lower the pH is going to be, and the greater the Ka. So the less it acts like a weak acid, the lower the pH. Now we need to understand what's happening in different areas of the graph. Now the lower region of the graph, this is our buffering region. Because we still have a large reservoir, so we have excess of the weak acid, and we've made some of the salt. In other words, in our example, some of the methanoic acid has reacted with the sodium hydroxide to make water, but it's also made now some of my salts. So now I have salt present as well as the excess weak acid. So that's why it can be acting as a buffer, because you've got the weak acid and some of that acid has reacted with the hydroxide to make the salt. Okay, the pH though at the equivalence point is about pH 9. It may be as low as 8, but it's certainly not 7. And the reason for this is because you're dealing with a weak acid. If you remember back to our notes on acids, the weaker the acid, the stronger the conjugate base. And because I'm dealing with a weak acid, it means that the base that you make from this reaction is strong. So we think what's actually present in the mixture at the equivalence point. Well, I have two things. I have water and I have my salt, CH3COO negative, Na positive. And those are the only two species present at the equivalence point because all of the acid has been neutralized and I've not added any excess hydroxide. So these are the only two things present. But this will dissociate in water completely to produce the CH3COO negative ions and the sodium ions. Now the sodium ions can't react with the water because they come from a strong base, but the CH3COO negative has come from a weak acid, and that makes it a strong conjugate base. Stronger, at least, than water. So we have C3O negative, add the water, and there will be a reaction. It's not a full reaction, it's still at equilibrium, but that salt would be able to pick up hydrogen ion from the water. Remember, water is amphoteric, so it can act as an acid or a base, leaving behind hydroxide ions. So this explains why the equivalence point of this reaction is not pH 7, because you produce OH negative ions. So the salt that you've made has a pH of about 9. At the upper region, again, it levels off. So this upper region is not a buffer, as there is no weak acid and its salt, or a weak base and its salt. So we're adding excess hydroxide ions. pH approaches its maximum, pH 13. So it looks a lot like a strong acid, strong base curve. The maximum pH is about 13. So there's one more important thing we can do with a weak acid, strong base curve, and that is actually to use it to work out our Ka expression. So if we look at the dissociation of formic, or otherwise known as methanoic acid, we have our acid HCOOH, and that dissociates to form the hydrogen ions and the HCOO negative. And again, you can write the Ka expression just as normal. So we have concentration of hydrogen ions times the concentration of the HCOO negative divided by concentration of the HCOOH. Rearranging this to find a concentration of hydrogen ions, we have concentration of hydrogens equals Ka times concentration of the acid divided by the concentration of the salt. And we want to know what special conditions does the concentration of the hydrogen ion equal Ka. In other words, we need to be able to cancel this term. So we need to know when does the concentration of the acid equal the concentration of the salt. And to understand that, we need to look back at our curve. So at the start of the reaction, and I'm going to call that start of the reaction here, you have all the acid you're ever going to have, and you have no salts, because you've made none of the salt yet, but you've got pure acid. You haven't added any alkali, you've just got all your acid. At the end point, at the equivalence point, at the end of the reaction, at this point here, you have no acid and all the salt you're ever going to make. So we know what happens at the start. In the start, let's say we have one acid and no salt. And at the end, because it's a 1-to-1 molar ratio, we have no acid, it's all been used up, and we've made all the salt we're ever going to make. So at half the equivalence point, that is the point at where the concentration of the acid equals the concentration of the salt, because at that point, I've got half and half. So if I started with one of acid, and obviously I've got no salt because I haven't made any, at the end point, all the salt I'm ever going to make has been made, and I've used up all my acid. So halfway between these 2 points, that is where we've got half and half, and that is where we've got equal amounts of both acid and salt. And that's why we can work out the pH. So the special conditions is at half neutralization, where half the acid has been neutralized and half the salt has been made. So if we have a look at our reaction between methanoic acid and sodium hydroxide, and then we can use our graph, or the graph you've plotted, Na positive, to work out the half equivalence point. So from the graph I've plotted, we can see that the volume of sodium hydroxide needed to neutralize half of the acid is 12.7 centimeters cubed. So that's my half neutralization, my half equivalence point. I can use that and just basically read off the graph. So I'm interested in this value here, and I can work out that the pH at this point at 12.7 centimeters cubed was 3.8. And I know, because of my equation, the pH equals the pKa at that point. So then I know that 3.8 equals the pKa value. Now to convert pKa into Ka, it's just 10 to the minus, if you remember. So Ka will be 10 to the minus 3.8, which gives us 1.6 times 10 to the minus 4 for our methanoic acid.